Hi, I'm Husky. I'm an indie game developer who's been working on an MMO using my own custom game engine. The previous two devlogs have been very gameplay focused, so today I want to go over something that I find quite interesting: pathfinding and navmesh generation. But first, I just quickly want to give a huge thanks to all the people who've donated since the last video. It means a ton and I'm very grateful. Even if it's not much, I appreciate it a lot and it helps me continue to make games and videos, so thank you. Now, if you've seen the first devlog, you'll know that for my physics engine, I'm using BSP trees. If you don't know what those are, I'd recommend you go check out this video by Matt's Ramblings, which goes very in-depth on what they are. He does a much better job at explaining them than I think I could. One big advantage of having a world that uses BSP trees is that we can use a very simple algorithm to generate navmeshes. However, that's a bit complicated, so I'll start at the beginning so that everyone's on the same page. So, when you have an NPC in a target position, maybe a player the NPC is following, how do you get the NPC to move to the target in a way that seems natural? A very simple starting point could just be to have the NPC walk in the direction of the target until their position is close enough. But this stops working once the world has obstacles like walls or holes that would cause the NPC to get stuck. There are algorithms out there like A*, which are designed to calculate the best route to travel given a set of connected nodes. So if we knew the positions of every walkable area on the map, we could use this algorithm to calculate a path between walkable positions, and then have the NPC walk between those to avoid obstacles. Unfortunately, this presents a challenge. How do we get those nodes? A naive solution would be to simply place those nodes manually in the map itself by hand. Some games, like SCP Containment Breach, actually do this, but in my opinion, it's way too time-consuming to be a viable solution for a game with a large map. The most common solution for modern games is to use something called a navigation mesh, or navmesh. Basically, we generate a 2D polygonal mesh that covers all of the walkable areas in a 3D world, and each polygon of that mesh becomes a node. We can walk freely within a polygon, knowing that all the spaces within it are walkable, and traverse between connected polygons, knowing that since they are connected, they can be walked between. This is a good solution, but presents one last problem. How do we generate the navmesh? There are a lot of solutions for this, but the method I use is, as I've said before, heavily dependent on the fact that my game uses BSP trees. I will also say that my method is heavily based upon this paper written by Stuart Golodetz in 2013. I randomly found it on Google and do not know anything about its creator, but it and the referenced Quake 3 Arena bot master's thesis by Jan Paul van Waveren were incredibly helpful in my own implementation. I've left a link to both in the description, and I hope that considering the age of these links, they don't end up failing to load in like 5 years. So let's start with a very simple idea. Any plane that faces upwards is a plane that can be walked on. If we visualize this, we can see that all the green areas are areas that we have determined are walkable, and everything else is unwalkable. Unfortunately, if we give this to an NPC, we'll see that they will try to walk through walls and fail because they collide with the walls. This is because the ground underneath the wall still exists, and the NPC sees the blocked ground as a walkable area and thus tries to walk on it. So here's our first challenge. We must figure out what areas the NPC can collide with and then somehow subtract them from the walkable area. Our NPCs use a fixed-sized axis-aligned bounding box for collision, and if you've seen the video on BSP trees that I talked about earlier, you'll know that we can inflate the world's planes in a way that allows us to simply ray trace a point through it to mimic the bounding box collision. So what we can do here is inflate the world, then subtract that inflation from the ground planes to get the ground planes that we can actually walk on. This, of course, is easier said than done. Unless you're familiar with Boolean operations on geometry, then you may not know how to actually implement this. Luckily, BSP trees once again come with a very simple solution for this. One of the main algorithms we use when generating the BSP tree is an algorithm to take a plane and a triangle and split that triangle into multiple parts using the plane almost like a knife. And we can actually really easily reuse this code to split each triangle by all of the other planes in the world. We simply determine if a triangle is intersecting one of the inflated planes, and then discard any part of it that ends up behind the planes. We can actually do this quite efficiently when using an actual shape to clip the triangle by converting the shape itself into a BSP tree, then using a recursive algorithm to clip the triangle using the BSP tree. Now this theoretically gives us a perfect navmesh to use for pathfinding. However, in practice, it has a few issues and extra things you'll need to implement in order to make it fully work. First of all, if we look at a naive approach to inflating the world by the bounding box's size, we'll see some very clear gaps in the generated geometry. This is caused by the fact that we're scaling each plane individually instead of scaling the object as a whole, which as far as I know, we can't really avoid. The way that the 2013 paper I mentioned earlier solved this, which is also the same way that I've implemented, is to scale each plane from its center by a large amount, then use that same BSP clipping code I mentioned earlier to remove any parts of the triangles that end up outside of the shape instead of inside. In practice, this also has one other issue that I'll discuss more in a second, but overall, this method seems to work pretty well. Although, if anyone else has any better ideas, then I'm very open to hearing about them, as I love learning about alternative methods of tackling a problem like this. Now, our second problem is the fact that due to all the triangle splitting we've been doing, the actual topology of the navmesh ends up looking worse than the topology of a 3D model from Garten of Banban. Now, I don't actually have a good method of solving this other than simply attempting to retopologize the world after generating the initial mesh. However, I've also found that in practice, this doesn't end up adding too much overhead to pathfinding. Although it's definitely something that will add a lot of overhead the larger your world is, so I'd say it's definitely worth to try and find a solution to this. The fact that these triangles can get so crazy also adds in an element of watching out for floating point imprecision. If you rely on any algorithms or equations that use division, be very careful to check that you aren't accidentally dividing by 0, as this will propagate a not a number floating point value throughout your entire calculation and definitely mess up some stuff. Now, while this method of generating nav meshes is overall very cool and technical, I won't lie, I can be a very lazy programmer sometimes, and because of that, my actual implementations of stuff can end up looking like drug-fueled nightmares of a 1990s id software programmer. And because I think that's funny, I'll also spend a bit of time self-deprecating by showing off some of my extra techniques behind nav mesh generation and pathfinding. First of all, remember that thing I mentioned earlier about the nav mesh topology looking awful? If you also remember the fact that we're scaling all of the planes, then clipping the edges, one thing you may have figured out is that the larger we scale these planes, the worse this topology issue gets. In fact, if I set the scaling value to 10, then the visualization often fails to load due to my GPU getting overloaded by the amount of tiny triangles I'm asking it to draw, and sometimes ends up freezing my entire GPU driver and requiring me to restart my computer. Another thing to note is that there's a lot of very inefficient or otherwise poorly written code in the pathfinding algorithms I made. When we start pathfinding, we need to figure out what triangle of the nav mesh we're standing in, and while I very easily could have tied this to the current leaf that the NPC is in within the BSP tree, I decided to be very lazy and instead just iterate through each and every triangle in the nav mesh and check each one to see if we're inside of it. And because I'm not currently retopologizing the nav mesh, this means that we could be searching through hundreds of thousands of triangles, running this costly calculation on each one to check if we're inside of it. I will 100% be fixing this in the future, however I've currently given myself the excuse of this is only ran on the server as to why I haven't done this yet. Because of this, as well as just the general slowness of A-star and other things that need to be done when calculating a path, I've actually gone ahead and structured the NPC pathfinding to take place on separate threads so that the game doesn't lag whenever an NPC tries to recalculate a path. Notably, this does actually use operating system threads and not Tokyo tasks, as the game world code runs synchronously, which I talked about more in the first devlog. Speaking of generating the path, one thing I haven't actually mentioned until now is how we actually generate the path itself for the NPC to walk along. A naive implementation would just have the NPC walking from the center of each polygon to the center of the target polygon. However, in practice, this will result in many edge cases where NPCs will end up trying to slide along walls or fall into holes. Now, I say naive implementation, however, my implementation isn't much better. Instead of navigating between polygon centers, I instead navigate between the midpoints of polygon edges. When we want to traverse to another polygon from our current one, we first find which edge connects the two, then find the midpoint of whatever edge is the smallest, and then set our target position to that point. I think my code definitely has some bugs though, as this still occasionally ends with NPCs getting stuck. However, I've solved this by simply faking everything and having NPCs interpolate their position to the actual target position once they're close enough. I love being lazy. By the way, I never mentioned one other thing that I found notable, which is how I figure out what polygons touch other polygons. The correct way to do this is to actually calculate the distance between edges of polygons, and then mark the edges with both their distance and their ability to be walked between. But I was really tired when I wrote the code for this and ended up doing a much simpler implementation. I simply make a slightly enlarged bounding box for each polygon, and then see what polygons that bounding box intersects with. And then I trace a ray from that point to the next, and if the trace doesn't hit anything, then it gets added to the list of traversable polygons. Surprisingly, despite the amount of corners I've cut throughout this entire process, the code actually works pretty well all around, and runs at a speed that I would say is completely manageable. I'll definitely be improving it in the future, but for now I think it works well enough for adding a very large amount of dynamic interaction to the NPCs. Since the last devlog, a ton of progress has been made on Lightless. I've implemented a lot of new features, and we're quickly approaching the point at which we'll be able to start doing public playtests. I'll talk more about this in the future, but if you want to be the first to hear about it, then I've left a link to my Discord server in the description. And if you don't want to punch me after seeing my code quality, I've also left a link down below for donations, since it's very much appreciated and helps a lot. Nothing's locked behind donations, but it's always very much appreciated. That's all for now. Bye.